Can you hear me? Your book has the answers to odd questions in the back. So I don't know which version you have. I've got a very old one. So the counting chapter is chapter 4. We pretty much do the entire chapter. So you should take a look at it, except for we don't do probability theory. So let's see, we don't do that. Yeah, so take a look at what's in your book. It's good. All right, so one way that people actually count things when you have a complex problem is to actually make what's called a tree diagram. And a tree has a root and a number of branches leaving the root and possible additional branches leaving all of the endpoints of the other branches. So it looks like this. You've probably seen a binary tree before. That's sort of a typical one. And what we do at each of the points is we make a decision. So this is an abstraction that computer scientists use all the time, is that we make a decision at some point on a diagram, and then we have lines representing the different options that we might have. So for example, let's say we have a problem that is how many bit strings of length 4 do not have 2 consecutive ones. So one way to do a tree diagram for that is to say, okay, let's start out. We don't have anything in the string yet. Let's assume that if we go this way, we start with a 0. You can put that label on the node. And if we go this way, we have a 1. So if I start out with a 0, I can have a 1 next, no problem, right? And then when I get a 1, I'm not allowed to have another 1, right? So then the next thing has to be a 0. There's only one choice there. I should have made a 0 go to the left just to be consistent. Okay, so if I get a 0, again, I'm allowed to have another 0. And a 1 is okay too because I don't have any 1s yet. So far I have 3 characters down to this length. So I need to get one more. If I have a 0 here, I'm allowed to have both a 0 and a 1. Here I'm not allowed to have a 0 or 1, so I have to have a 0. I can have both options here. And again, I can have both options after the 0 on the right, both options after this one. So what you would do to figure out your string, this is all the possible strings, but to read all the possible strings, you read from the top of the diagram and then read out the labels on the nodes. So your first possible string is all 4 zeros, and then if we do a depth first search, we would get all zeros and then a 1. And then we can get 0, 0, 1, 0. That's one way here. Then I can read the left branch here, 0, 1, 0, 0. Read the right branch, 0, 1, 0, 1. Read this. We start with a 1. Then we have to get a 0. Go to the left, 2 zeros. Go to this one. Go to the right. So we start with 1, 0. Then we get 1, 0. And that should hopefully be all of them. So in general, this is a way that we draw a diagram for counting things or for enumerating all the different things that might happen. The problem with tree diagrams is they are big. And also, they're usually not regular. So this is not regular because it doesn't have the same number of children at every node, right? So it's kind of hard to count that. I have to actually count all the paths to figure out how many different combinations there are. So I actually have to read everything in the entire diagram to figure out, and that's kind of a pain. So tree diagrams are something we use to start getting started, like recognizing all the different things that might happen and thinking about paths, like breaking down the problem into a series of decisions and then thinking about all the possible options at each of the next stages. Like I get one character, and then based on what I have so far, what can I have next? That's what the tree diagram is for. So I'm showing it to you because it's an abstraction that you can use for when you're trying to list out all the possible combinations of something when you're doing a counting problem. It's not generally something that you use for big problems. For example, even for strings in the English language, we don't want to draw this, right? Why don't we want to draw one of these? There's 26 branches at any point, right? And then if you allow capital letters, that's definitely not fitting on my page. So we don't want to do these in general. However, it's a good idea to do them to make sure that you understand the problem. So that's really why we do them, is to make sure that you're really understanding, okay, if this is what's going on, let me draw a picture and make sure that I know what all the decision points are. And then you can satisfy yourself that you know what's going on. We can do tree diagrams for things like playoffs. You've seen those, right? So that's a more typical way that you actually might use a tree diagram. And there's an example in your book, and I'm not going to draw it. So here it is. Love overhead projector. So this is a tree diagram for the best 3 games out of 5. And we need to draw this, though, for a playoff. Why do we need to draw it for a playoff? None of you watch any playoffs at all. You're computer science majors, so in your free time you watch Twitch. Okay. You want to see all the possible options. Like if my team makes it to the next round, how many more rounds do they have to make? So you want a tree diagram for that because you want to see all the possibilities at the same time, so you can follow all the paths. So sometimes a tree diagram is exactly the thing you need. And for binary strings, it's not that bad. So for binary strings and for things like playoffs, highly recommend tree diagrams. We also use tree diagrams when we are talking about games. And before you get too excited, we're talking about games like chess or checkers or tic-tac-toe, where we often make a tree diagram about the options that a player might have. So one level of the tree would be all the different things that a player could do. So they'd have nodes for all the different moves they could make. So like in chess, each node would actually be like a picture of the board after somebody did their move. And then the next layer would be what that player could do. And we do what's called min-max estimation to figure out like what people are actually going to do. So you make this tree of all the things you could do, and then you kind of assign a score to every board for each player. And it's called min-max theory because I'm trying to maximize my score while I minimize yours. So for 2 players, we often use tree diagrams for actually looking at all the possible ways the game might play out. And the way we give a score is actually by estimating, like, if I were to follow this path down to the end, how many of the outcomes actually are wins and how many of them are loses. So it's a cool application that I wanted to let you know about because you do use it later if you want to do something like game theory. So we don't use that for things like first-person shooters or things in 3D worlds because there's too many options. Again, just like trying to use a tree diagram for strings, it's just not going to work. So, however, there are a lot of research projects going on where people are trying to understand what behavior people do have in complex environments and then try to use that to give, hints or feedback or even just classify people by the behavior that they have. And that's really interesting stuff. But don't do it with tree diagrams. Okay, I just wanted to mention it to you because you should know about them because they're extremely useful sometimes. Okay, now we're going to do a problem that is part of combinatorics called Ramsey theory. And we're not going to do all of Ramsey theory or even give a definition of it, but Ramsey theory is about the distribution of subsets of elements of sets. So we're going to do a fun problem. So the problem is, assume that in a group of people, each pair of individuals is either two friends or two enemies. It's like back from high school. Show that there are either three mutual friends or three mutual enemies. There was a question? Yes, I'm sorry. I think I said it but didn't write it. So we have a group of 6 people. Each pair of individuals is two friends or two enemies. Show that there are either 3 mutual friends or 3 mutual enemies. Do we have any ideas of things we've learned so far about counting that might apply? Is this a product rule problem? Tree diagram? No. Didn't you see how many pages I turned? I'm just kidding. Yeah, we could draw some dots. But the things we've learned so far are product rule, right? Union rule, product rule, combinations, permutations, and the pigeonhole principle. Out of those 5, do any of those sound like what we're looking at? Pigeonhole principle. That's the first thing you need to do is figure out if a problem is a pigeonhole principle. If we could show that there's some minimum number of something, you're looking at a pigeonhole principle problem. And by the way, you're allowed to abbreviate it as PHP. So when we answer a question using the pigeonhole principle, you have to say, by the pigeonhole principle, blah, blah, blah. So what we're going to do now is let's look at one of the people. Okay? And how many people are in the rest of the group? There's 5 people left. Now, if we divide those people into A's friends and A's enemies, we can do that because every person is either a friend of A or an enemy of A. If we divide it into 2 groups, we know by the pigeonhole principle that there are 5 people, so that's going to be the pigeons. And these are the 2 groups. So there are 2 of them. So by the pigeonhole principle, if I divide those 5 people into 2 groups, that there's a group that has 3 people in it, right? So there's either A either has 3 friends in the group or 3 enemies in the group that's left. Okay, so let's look at the idea where we have 3 friends. Let's say we're just going to do the case 1. There's 3 friends, and let's call them B, C, and D. Now, when we say mutual friends, what does that mean? If 3 people are mutual friends, what does it mean? They're all friends with each other. That means all pairs are friends. So, like if I said A, B, C are all friends, then A is friends with B, and A is friends with C, and B is friends with C also. And is the friends relation, is that symmetric? Yes. It is symmetric. Yes, right. It depends on if you're talking about Facebook or not, right? Okay, so we have 3 friends. Now, if any two of these are friends, then they're already friends with A, right? So if any two of them are friends, then we've got a group of 3 mutual friends. And let's just call those B and C. So then A, B, and C are mutual friends, right? If no two of them are friends, then what happens? And how many are there? Then they are mutual enemies, right? So we've actually broken it down. So if any three, if the 3 people in the group of 5 are all friends of A, then either 2 of them are friends and then there's a group of 3 mutual friends, or none of them are friends and there's a group of 3 mutual enemies. And there's a mirror case for if the case 2, that there's 3 of A's enemies. It's a mirror case, so you just reverse the words enemy and friend and you prove the other case. This is sort of like a tree diagram, right? It sort of is because I'm breaking down all the cases step by step. But it's not quite a tree diagram because I can't put all the possibilities. I'm not drawing all the possibilities because it's too many. So, how many people feel like they could do the mirror case? 1 person. Okay, since you don't feel like you can do it, let's do it. Okay, so prove case 2. In case 2, there are 3 enemies. In the 5 people left. So we're also going to call them B, C, and D. Okay, so I want you to work that, and then we'll check our answers. Yeah, so it's pretty much you copy the last one over, except you change the word friend into enemy and vice versa. So what we're doing is we're trying to think of all the different possibilities of what might happen. So in the pigeonhole principle, we know that we have some categories and there has to be a certain number of people in each category, and then we think about each of those 2 categories. So if I have 3 people in one category, then I figure out what would happen. So again, this is similar to truth tables in that when we do cases, we're listing all the possible cases. So once we had case 1, we had 2 possibilities. Either any 2 are friends or none of them are friends. And then we have the same thing going on for case 2, is that there were 2 other possibilities. So what we're trying to do when we do counting is to break down all the possibilities of things that can happen. And that's what we're doing with these problems. So let's do another problem. It won't be exactly like this. Well, I can do one that's closer to this so we can talk about it. Okay, so show that out of any group of n plus 1 numbers, there must be 2 whose difference is n. So we obviously were just doing pigeonhole principle stuff, so the problem's obviously a pigeonhole problem. But if you're doing your test and you're looking at problems, if it says show that there must be some number of something, it's always a pigeonhole principle problem. Okay, so what does it mean to have 2 numbers whose difference is n? Yes? No. Yes. So, I'm sorry, I meant a multiple of n. Yes, it is like mod. So, can you elaborate on mod? That's right. So I can get a mod if I divide some things by something. I didn't hear if you said actually what we're dividing by. What do we divide by? So we divide each number by n, and then what do we get? So when we do a pigeonhole principle, so you're right, but when we do a pigeonhole principle problem, what we have to do is identify the pigeons, identify the holes. Okay? So the pigeons are, that's the numbers. And so there's n plus 1 of them. And the holes are what? The remainders of those numbers mod n. So those holes are 1 all the way up to n, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then all the way up to n. Or you can start at 0 and go all the way up to n minus 1. It's just easier to count stuff if you start with 1. So as any of you have written any programs at all, know we make less errors if we start with 1 than if we do if we start with 0. Okay? So how many holes are there? There are n of them. So if 2 numbers have the same remainder mod n, if I subtract them, so if a mod n is equal to b mod n, then a minus b equals what? It's a multiple of n. So now by the pigeonhole principle, n plus 1, that's the number of pigeons, divided by n, which is the number of holes, which is remainders mod n. They have the same remainder mod n, so therefore they have a difference that is a multiple of n. Okay, here's a good question. Are these consecutive numbers? The list of numbers? No, they don't have to be. We can prove some really cool stuff with the pigeonhole principle, stuff you're really surprised about. And whenever I took this class, Dr. Bitzer told me, he would use one of these problems to win bets at parties all the time. Let's see if I can find it. Here's one. It's that time of year you need some extra money, right? Okay. I think when he was younger, people talked about baseball a lot more than they do now. So here's a baseball problem. Okay, so we have a month with 30 days, and a baseball team plays at least one game a day. But no more than 45 games. They can play a lot because they're mostly standing there, right? Okay. So what we're going to do is show that there must be a period of some number of consecutive days during which the team must play exactly 14 games. When you just say that, you're like, that's ridiculous. You can play any number of games on any days. How can you guarantee that there's exactly 14 in some consecutive number of days? It sounds crazy that you can do that. So it involves a trick. So what we're going to do is we're going to make a variable. We're going to make a variable for the number of games played on or before the jth day of the month. So we're going to make AJ equal A sub j, the number of games played on or before day j in the month. So that means like A1 is how many games you played on day 1. A2 is how many games you played on day 2 plus how many games you played on day 1. A3 is the sum of the prior ones plus however many days you played on day 3, and so on. So we have a sequence of 30 numbers. Now, since there's at least one game on every day, there are no two numbers of those that are the same, right? They're all different because all of them, we play at least one game every day. So every day, every number is distinct. Yes? Yeah, we're not saying one per day average, at least one game every day. That's what allows these numbers to all be different. So they have to be different because all of them is a sum, and there's at least one game every day, so all of them is at least one more than the last one. Okay, now what are we actually looking for when we ask this problem? So if we're looking for that there must be a period of some number of consecutive days where there's exactly 14 games, then that means that we're looking for one of these numbers to be exactly 14 more than one of the other ones, right? So how we represent that is just by actually making a list of all of these numbers, but add 14 to each one of them. So this is the list of numbers I'm actually looking for. So I want to prove that one of these numbers between A1 and A30 is actually equal to one of these numbers in this list. Now, there are 60 numbers in these two lists, right? Because each list has 30 numbers. So we have 60 total numbers. A30, though, is less or equal to 45, right? Because that's what the problem said. We don't play more than 45 games in the 30 days. So how big is A30 plus 14? If you add 14 to both sides, we get 59. Okay, so we have 60 numbers, and all of them are less than or equal to 59. If there weren't 2 days where the difference between the number of games is 14, then all these numbers would be different. So all the numbers in the first list and all the numbers in the second list would be different, right? However, by the pigeonhole principle, we can prove that 2 of these numbers are actually the same. Because I don't have 60 different numbers. I only have 59 possible numbers that they can be, because the lowest one has to be 1 or more, right? So there's only 59 possible numbers. That's the holes, right? And the pigeons is the number of numbers that we have. So by the pigeonhole principle, we have the ceiling of 60 over 59 equals 2 numbers that are the same in these 2 lists. But we know that none of these in the second list can be the same, and none of those in the first list can be the same. So the 2 that have to be the same is 1 from the first list and 1 from the second list. So we have to have 1 in each of the lists, and if we do, then the difference between those 2 days, whatever the sublabels are, is 14. This is a really standard trick for counting. If you want to show that the difference between 2 things is something, you either use mods or you add, copy the list over and add the thing you want the difference to be. Well, if you want to hear a master storyteller, you should go to one of his lectures. Dr. Bitzer is a master storyteller. I am not, so I'm just good at math. My son thinks I tell good stories, but did anybody see the Croods movie? Yeah, is it the Croods? Yeah, the dad tells a story every night and everybody dies. My stories are like that, except nobody dies, but they're the same. Okay. All right, let's do some more counting problems. Okay, let's do, well, actually I have to tell you about this. Okay, how many people have seen Pascal's triangle? Okay, cool. Thank you. Oh, that's not in focus. Okay, so this is Pascal's triangle, and it corresponds to the coefficients of a plus b raised to the n. And where n is the row, so this is n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. And the coefficients are, so the first one is always a raised to the n, the last one's always b raised to the n, and in the middle is in decreasing the number of a's and increasing the number of b's by 1 every time. So this one would be a to the 5th, this would be a to the 4th b, that's a cubed b squared, so notice all of them add up to 5, and then a squared b cubed, and then a times b to the fourth, and then b to the fifth. So that's just an example of how we go across Pascal's triangle, but that actually tells me the coefficients for each of those terms. Yes? Yeah, 1, 1. Sorry. There's a 1 above for n equals 0, but that doesn't do anything, so we'll just get rid of that. So it's really helpful for expanding a polynomial that's a sum raised to the nth power. Very, very useful. So these numbers actually correspond to some combinations, surprisingly. So wherever I am in this combination, each of these correspond to binomial coefficient. Let me go to there. So here's the nth row. It's going to be, if I'm in the nth row, the numbers in the row are n choose k, where k equals 0, 1, all the way up to n. And n choose k is another way of writing this, which you'll probably see on your scientific calculator. And that's how you read it, n choose k. So n is the number of things you're choosing from, k is the number of things you're choosing. When you write it this way, you're assuming that order doesn't matter. That's combinations. So let's look at that. So this first number is, n is the number of things I'm choosing from. So the first number is 5, choose 0. Second number is 5, choose 1. Third number is 5, choose 2. 5, choose 3. 5, choose 4. And 5, choose 5. So when we choose 0 of something, there's exactly one way to do that. That is a definition. It is not, there's like a bazillion ways you could do nothing. But when we're counting things, we only count it as one way. Because it's all we care about is how many choices we have, and we have exactly one choice of nothing. The choice of the empty set, there's only one way to get that, by choosing nothing. So that is 1. 5, choose 1. So what is this bottom number actually counting, if you look at the pattern here? It's the number of B's. Okay, and we all know, or hopefully, you actually know the way you get this is by adding those numbers that are above, right? Why does that happen? Does anybody know? Let's figure out why. So this is going to be, if we use first, outer, inner, last. So first is here. The outer is AB, right? Inner is BA. And last is B squared. So that's actually how we get A plus B squared. It's by using the FOIL method, first, outer, inner, last. But if you look at it, all the terms, I'm actually choosing some terms from each of these, right? So out of these two, I'm choosing a term to go here and a term to go there. And so these 4 different ways are all the ways of choosing one term from each of those. So there were 2 ways to choose here and 2 ways to choose there, so I get 4. Okay, then we multiply that. Well, let me just add that together. So we get this. Then when we're multiplying these, I multiply this A by all of those. So I'm going to get a cubed plus 2a squared b plus ab squared. And then I'm also going to add all of those with a b on them. So the terms that have, like, let's say that they have a an AB in them. So we don't have any ABs left. We have AB squared. So what are the ways to get AB squared from this? And this. So it came from either I can have 2AB, so we came from the 2AB term and multiply it by a b, right? Or we can start with the b squared term and multiply it by an a. So that's why the previous numbers, so this was a number from the previous layer of the Pascal's triangle. So the 2AB had one a and one b, so then if I can pull the other b from here, that's what I do, and then the end term, the 1, had a b squared. So that's why we're going to end up adding those two, because the 2ab term was here and the b squared term was there. Then we multiply by a to get that, and we multiply by b to get that. So that's why the coefficients add up the two previous ones. It's just something good to know about combinations. And so another way we can write that Pascal's identity is actually that so these are the two terms right above a term that add up to it. So we won't use it for anything we test you on. It's just interesting. There's also another interesting thing with combinations, and that is that the sum of all the combinations from k equals 1 to n, 0 to n of CNK is 2 to the n. Is that surprising? Not at all to people who already know it. Okay, so the proof of this goes back to our power set argument. Okay? So C and K is actually, I have n items I'm going to choose, and I'm going to choose k of them, right? So choosing 0 of them, that's the empty set, right? So it doesn't equal that. It's just the set that we're choosing. The stuff that we're choosing is the empty set. If I choose 1, then I'm choosing just one element. So there's n ways to do that, right? And then ways to choose 2 of them, that was like when we chose pairs of our sets. So remember we were doing power sets of something like AB, and then we wrote down the empty set, the set containing A, the set containing B, and then the set containing the pairs. And this is the power set. So for the number of elements that we have, n, there's 2 to the n elements in the power set. But that's exactly what this says. Because each term of this is telling you about the size of, it's telling you about the different sizes of sets. So choosing 0, that's the empty set. Choosing 1, that's all the 1-element subsets. Choosing 2, that's all the 2-element subsets. Choosing 3 is all the 3-element subsets, and so on. So that's why it adds up to 2 to the n. Remember that the reason why that it adds up to that is we mapped that power set problem onto a binary string problem. So for all the elements that I have, let's say I have the elements 1 up to n, and let's do a problem that we can actually look at, that we actually make a place for whether that element is in the set or not. So all of the sets can be represented by a 0 or 1 in each one of these blanks that tells me whether or not that element is present, and then that's 2 possibilities per blank, and we multiply them all. So that's why this adds up to 2 to the n. So there's all kind of parallels between a lot of the stuff that we've done this semester, even though it all seems completely disjointed. It's actually not. There's lots of relationships between the different things that we're doing. And then to show one more relationship there, to go back to the subsets, let's actually look at the power sets. So that's the one element. Sorry, that's the 0 element. There's nothing in there, sorry. If we draw levels of subsets for 1, 2, 3, 4, I'm going to run out of room. I'm going to get rid of 4. Okay, we're just going to do that. So this is all of the subsets of the set 1, 2, 3. So what we just said basically is that there are 2 to the n subsets here. So n is 3. And that should be the size of the power set of S. So it should be 2 raised to 3, which is 8. Do we have 8? 1, 2, 3, 4, 5, 6, 7, 8. Good. So we have 8 elements. And then if we go back to our subset relation, the empty set is a subset of each of these, right? So I can actually think of each of these as a node in a graph, and I draw a line in between them if they relate. I'm not drawing an arrow because I'm going to assume all the arrows go up. So 1 is a subset of 1, 2, and it's a subset of 1, 3. 2 is a subset of 1, 2, and of 2, 3. And 3 is a subset of 1, 3, and it's a subset of 2, 3. And all of these doubles are subsets of the triple. So each of the number of elements on each of these is 3 choose 0, 3 choose 1 number of elements, 3 choose 2 number of elements, and 3 choose 3 number of elements. So this is just a picture of the proof that if you add up all these numbers, it goes to 2 to the n. Yes? This is a Hasse diagram, and it's also the relation, the subset relation is a partially ordered set. And if you look at this the right way, it's almost a cube. It's a little bit squiggly, but do you see that it's almost a cube? And remember that before we actually talked about gray codes where we could actually draw this kind of cube, and then all of the links that we had drawn were differs by 1 bit. So we could actually go through all the strings from 0 to 2 to the n minus 1 by actually drawing a cube like this. So it's actually all the same problem. So if I represent each of these with a string of zeros if an element's not there, and a 1 if it is there, so I'm just drawing the bit string. Sorry, that's a 0 right there. So those are the bit strings corresponding with each of those sets where I have a 0 for a 1. Sorry, a 0 if the element's not there, and a 1 if it does. And so each blank is a 1, 2, or a 3. So those are the representations. Now, any path through here is called a gray code because all of the adjacent nodes are different by 1 bit. So everything goes together in the whole class. Nobody's excited like I am, but that's okay. What'd you say? It doesn't make the final easier. Okay. So this is a Hasse diagram. For the power set of S and the subset relation where S is equal to the set containing 1, 2, and 3. So a Hasse diagram it is a bigraph for a relation, but all the arrows go up. We don't draw the reflexive edges that basically are circles on the little elements because the empty set is a subset of itself, but I'm not drawing that. And I'm also not drawing that the empty set is a subset of all these ones up top because they're already connected to the lower levels. So a partially ordered set is transitive, so if I have a connection between these two and a connection between those two, the diagram actually would have a line up there if I was drawing all the possible relations. But we're trying to make it simpler. That's what Hasse diagrams do. We make all the arrows go up, and we skip all of the transitive edges, and we get rid of all the reflexive edges. Okay, let's do some more other counting problems. Okay, here's another one. So a company has products in a warehouse on aisles of shelves with bins on the shelves. There's 50 aisles, 85 horizontal locations for bins on each aisle, and 5 shelves all through the warehouse. What's the least number of products the company can have so that at least 2 products must be stored in the same bin? What kind of problem is that? Pigeonhole. Because we say there's least number and some things have the same something. So it must be a pigeonhole problem. So that's your first thing, is to figure out if it is one or not. So then we actually need to figure out, so products must be the pigeons. And we know that the ceiling of the products over something is going to be 2, because that's what comes after the words at least. So, and we want to find the least number of products, so we have to also figure out what the holes are. What are the holes? Whatever comes after the word same is the holes. So in order to prove that there's at least 2 items or 2 products in the same bin, I have to have less bins than holes. I'm sorry, less bins than products. That's what the pigeonhole principle says. So I have to have fewer holes than I have pigeons. In other words, fewer bins than I have products. So we need to figure out the number of bins, right? How many bins are there? I have to combine those numbers, 50 aisles, 85 locations for bins, and 5 shelves. What do I do with those numbers? Multiply them, because it's the product rule, because I have an aisle and a horizontal location and a bin, a shelf. So I multiply all those, use the product rule. That's a large number. I don't care what it is. Okay, so how do we get that the ceiling of some number over this is actually 2? What's the smallest possible number that can make the ceiling go up to 2? That number plus 1, and that's the answer. So products, so the minimum number of products, so we can guarantee this equals the number of bins plus 1. In other words, 50 times 85 times 5 plus 1. Yes? We always use the ceiling in the pigeonhole principle, so the question was, how do I know if I need to use the ceiling or the floor? I always use the ceiling in the pigeonhole principle because that's what it says. And the reason is, remember that when we talked about the introduction of the pigeonhole principle, we said when we try to figure out stuff with the pigeonhole principle, we assume the most even distribution possible. So when we use the pigeonhole principle, what we're assuming is we distribute everything as evenly as possible, and then we have some darn thing left over that we have to stick in one of the bins. So that's why it's the ceiling, because it's like the tipping point before you, after you go to the next number. So it's always the ceiling for the pigeonhole principle. Okay, let's do another one. Okay, how many different bit strings can be transmitted if the string must begin with a 1 bit and it must have 3 additional 1 bits for a total of 4. So we're going to have exactly 4 1 bits. And we have a total of 12 0 bits. And we have to have at least 2 0 bits following each bit. So this is a case where we need to draw a good picture. So every time I have a 1 bit, I have to have 2 zeros after it. So I might as well think of that as a unit. So there were 4 1 bits that we have to have, so we have to have those. And it looks like we have to have a total of 12 0 bits. So what's the total length of the string? Okay, so we have these little units we have to have. So if we have to have those in there, how many other bits do we have left? How many numbers have I drawn on the screen? There are 12. How many numbers are there if I take out 12 from 16? Thank you. And what do those bits have to be? They have to be zeros. So now what do we do? So what we have is we have to have these chunks, plus we have to have 4 more zeros. So we have to have like places for these, and then we have to have 4 other places. We need to figure out how many places are there now. So I've actually grouped these together, so now if I move them around, they're stuck. So how many places do I have now? I've transformed it from 16 places into how many? There's 8. And what do we know about one of the places? The first one has to be 100, so in fact, I actually cannot think about this one and just look at 7 places, right? For placing things, because 100, I get no choices, so I'm just going to fill those out. And now I want to pick out where I put my 100s. So what kind of problem is this? Sort of like a divider problem. So we've already done some of the transformation that makes it actually not a divider problem, right? So we've actually now said that we have 7 places to choose, and we just need to figure out where we're going to put the 100s, right? So now we've actually said, okay, 7 places, I'm going to pick 3 of them to put the 100s. And then zeros automatically go in the other places, right? Now, the only thing I have to check out now is to figure out if any two different choices of putting the 100s down actually result in the same string. So I didn't work this problem before class, so I'm not actually sure if we're done yet. So we always have to check to see if we're done, because we did a mapping of this problem to something reasonable, but I'm not sure if when we put the 100s down, what actually happens with them. So what we need to do is make some sample strings. So if I put, let's see, we already have a 100 at the beginning. So if I pick 100 in those two blanks, is there any way that I could have chose another thing and get these here? There isn't another way. So if I just put some more zeros in between some things, I can't get those ones just two zeros apart. So that makes me feel pretty good. So what about if I do 100 and then I put a 0 and then 100? I think that's the only way I can get that. So I'm starting to be somewhat sure that what we have is correct. So let's see what the answer in the back of the book says. Okay, they just said it's 35. So let's see if that's correct. So C73 is 7 factorial over 4 factorial, 3 factorial, which is 7 times 6 times 5 over 6, which is 35. Yay. So what I have to do once I figure out how to map this problem is make sure that I'm not counting anything twice. And so that's why I was drawing this picture, to see if there was any way I could get the same thing by putting zeros and 100s in different spots. Let's do one more problem. Actually, I'm going to try to quickly do two. Okay, so how many bit strings of length 10 have 5 consecutive 1s or 5 consecutive 0s? So there's a trick to mapping this problem to count it really easily. So I'd like you to get started on this problem and see if you can draw a picture that represents how you might start counting the strings that have 5 consecutive 1s or 5 consecutive 0s. So there's my first picture. My first picture is I'm going to put all the 1s at the beginning. And then I'm going to put some blanks for whatever follows that, because I don't care. And then my next one's going to be, let me just move those 1s over 1. And let me just keep doing that, because a pattern is a good thing. Okay, now you might think if we just count up all these things, well, let's just do that. So each one of these choices, each one of these blanks has two choices, a 0 or a 1 in it, right? So this one, the number of ways to make that string is 2 to the 5th ways, right? Now the second one, the next one, I've specified 9 of the bits. What about the first one? It can't be a 1 because I have already counted that in the line before. So it has to be a 0 right there. So there's 2 to the 4th different ways of doing this one. Now the next one, how do I make sure that that one doesn't overlap with something already counted? What'd you say? The second position has to be a 0. So what I've done is refined my definition of my string is this picture is now a picture of all the different ways to have 5 consecutive 1s in a string. where the 5 consecutive ones start in a particular position. So this actually describes all of the bit strings where the 5 consecutive ones have to start in position 2. And if I do that for the whole diagram, then basically I'm copying this pattern of putting a 0 out front. And then the rest of these are 2 to the 4th because I'm allowed to have whatever in those blanks. Because once I put a 0 in that leading position, then the 5 consecutive zeros can't start before that. So this solves the problem of the 5 consecutive ones. And so what do I do with all these numbers that are on each of the rows? I add them. Now doing the zeros is exactly the same except you flip all the bits. So the number is exactly the same. So you add those two because that's an either or. But then you have to subtract all the things that could have been counted among the strings with 5 zeros and 5 ones at the same time. There's only one string like that, right? There are 2. You're right. 5 zeros and then 5 ones, or 5 ones and then 5 zeros. So I'm not going to talk any more about that one. I did want to show you one more problem. This is a homework problem, by the way. So you have to figure out the rest. The last one I wanted to do, and we're done with time if you need to go. I apologize. But I did want to tell you this because I have a trick for doing these lottery problems. So the trick is, when we're doing a problem that has multiple stages, when we need to choose winners then of something, and order matters, it's actually quite confusing to choose some things with order and then choose some things without order and then merge those things. It's really confusing. So what I highly recommend that you do is do what I would actually do maybe if I was awarding some winners to prizes, is actually figure out who all the winners are, get them to come down front, and then reorder them according to which prize they get. So I have 100 tickets and 3 prizes. I want to know how many ways there are to award prizes if 31 wins and 63 loses. So for the winners, how many possible winners do I have? So I have to choose 31. So this is choosing the 31 as a winner. Okay? Now I want to choose the other winners. So I've already chosen 31, so there's 99 people left. But now we know 63 doesn't win, so there's 98 people left. I'm going to choose 2 of them. And actually, just to be consistent, I'm actually going to say out of the 63, this is the 63 group, I'm going to choose none of them because he's losing. The reason why I did that is now the n's all add up to 100, right? And the k's all add up to 3. So the n's are the ones I'm choosing from. I'm choosing from 100 total, but they're in different categories. So there's a person who's winning, there's a person who's not winning, and then there's the other 98 we don't know anything about. Once I do that, I'm going to multiply by all the ways to rearrange 3 winners. So the first phase is to choose the winners, and I have this information about who wins and who doesn't, and then the second phase is to do the ordering. I highly recommend you break any problems like this.